The projectile hurtles across the frigid atmosphere at precisely 823 meters every second. Contact occurs. Hardened steel collides with hardened steel at a 60-degree deviation from perpendicular orientation. Every mathematical prediction suggests deflection. The round ought to bounce away from the angled protective plating like a skipping stone, dancing across liquid surfaces, careening harmlessly into the Ukrainian soil. The fighting vehicle's operators inside the Soviet T-34 prepare themselves for yet another glancing strike they have endured countless times previously. However, this particular round refuses to deflect. The malleable metallic covering at its forward tip collapses upon contact, expanding outward like some horrifying fungal growth pressing against the tempered armor plate. During the infinitesimal fractions of time preceding penetration, the deforming covering accomplishes something that contradicts the established principles of angles and the scientific laws governing deflection. The round rotates not in the direction away from the protective barrier as conventional physics would anticipate, but instead pivots directly toward the surface, adjusting its path to become perpendicular to the target. The bottom portion of the round experiences substantially greater opposition than the top section, generating an unbalanced force vector that rotates the complete projectile into the most favorable penetration trajectory. What transpires in the following moments transforms everything about armored combat. The 75mm round drives completely through 45mm of angled Russian armor, plating that theoretically should have delivered 90mm worth of protective capability. Within the rotating fighting compartment, an ammunition handler extends his reach toward additional ordnance. The metallic scream of armor breach represents the final auditory sensation his consciousness registers before hypersonic steel shards saturate the confined space with lethal fragmentation. The projectile's malleable forward covering, now utterly obliterated, has fulfilled its intended function. The reinforced penetrating core continuing behind it proceeds through the opposite barrier, departing the vehicle in a cascade of liquefied metal and human remains. From his observation point, 300 meters distant, the German artillery operator observes through his magnified optics. He anticipated a deflection. Instead, combustion smoke billows from the T-34's escape hatches. His superior officer's transmission crackles across the internal communication system, filled with urgent incredulity. You achieved penetration at such an oblique angle? The gunner offers no verbal response. He has already begun rotating toward the subsequent target. Another Soviet T-34 displaying its purportedly invulnerable sloped frontal armor. The identical 45-degree protective configuration that has successfully deflected numerous uncapped rounds previously. The identical revolutionary engineering that Soviet designers guaranteed would render German weaponry ineffective. He discharges another round. Identical outcome. Something fundamental has transformed in the scientific principles governing armored conflict. The malleable covering, originally engineered to prevent the projectile from fragmenting during impact, has evolved into an inadvertent geometry-defying instrument of destruction. Design engineers failed to anticipate this secondary consequence when they incorporated the covering to eliminate projectile disintegration at extreme velocities. They addressed one technical challenge and unintentionally resolved another. The round normalizes its trajectory. It pivots into the armor rather than away from the surface. The angled plates that should multiplicatively enhance protection, instead, become vulnerable to perforation. The meticulous Soviet mathematical calculations regarding effective thickness derived from elementary trigonometric formulas are suddenly catastrophically incorrect. Throughout field maintenance facilities spanning the eastern battlefront, German metallurgical specialists examine recovered projectiles, quantifying the deformation characteristics, attempting to comprehend what they have accidentally created. Soviet engineers conduct parallel investigations from the opposing perspective, analyzing perforated armor sections, measuring entrance trajectories, witnessing their defensive strategy disintegrate with each impossible penetration. This narrative explores how a malleable metallic covering fundamentally rewrote the established regulations of armored warfare. Continue following this account, because what superficially appears as straightforward metallurgical science actually represents a revolution in mechanized killing technology. June 1941 witnesses Operation Barbarossa unleashing 3 million German military personnel into Soviet territory. The Wehrmacht anticipates encountering inferior fighting vehicles. Instead, they discover T-34 medium tanks. The Russian armored vehicle embodies a radical engineering philosophy that German technical experts had previously dismissed as theoretically unsound. 45 millimeters of protective plating, positioned at 60 degrees from vertical orientation. Elementary trigonometric principles indicate this arrangement delivers 90 millimeters of effective defensive capability against perpendicular strikes. The German Panzer Mark III and Mark IV vehicles carry 50 to 80 millimeters of vertical armor configuration. Theoretically, on documentation, the angled T-34 should possess significantly superior protection. More critically, the angular configuration should cause most projectiles to ricochet harmlessly away. Soviet designer Mikhail Koshkin had extensively studied every accessible document concerning armor geometry preceding his death in 1940. His mathematical work was extraordinarily meticulous and precise. A projectile striking at 60 degrees from vertical orientation must penetrate through nearly double the actual plate thickness. The effective armor multiplication factor equals 1 divided by the cosine of the impact trajectory angle. At 60 degrees, that produces a multiplier of 2. 45 millimeters effectively becomes 90. However, Koshkin and his engineering team formulated a critical assumption that would prove fatally flawed. They presumed projectiles would maintain their original trajectory following impact. They assumed the fundamental laws of reflection, where incident angle equals reflected angle, would remain valid for high-velocity steel penetrators. Their assumption was completely wrong. Not because their mathematical calculations contained errors, but because German metallurgical specialists were simultaneously addressing an entirely different technical problem that would accidentally nullify Soviet armor advantages. Throughout 1941, German anti-tank artillery weapons were experiencing catastrophic operational failures. The Pak 38 50mm gun, engineered to discharge armor-piercing ammunition at velocities exceeding 823 meters per second, was shattering its own projectiles during target impact. The hardened steel tips designed for maximum penetration capability were excessively brittle. At extreme impact velocities, the kinetic shock of collision fractured the penetrator before it could defeat the defensive armor. Uncapped armor-piercing rounds were penetrating only twice their caliber at close engagement ranges. 100 millimeters for a 50mm projectile at 100 meters distance. This performance was inadequate against the newly encountered Soviet armored vehicles. German ordnance engineers at Krupp proposed a solution borrowed from naval artillery applications. Incorporate a malleable steel covering onto the projectile nose. The covering, fabricated from reduced carbon content steel with diminished hardness, would deform during impact, cushioning the shockwave and preventing the hardened penetrator from fragmenting. The malleable cap would redistribute impact energy laterally along the projectile body rather than concentrating force at the tip point. Initial testing at Kummersdorf proving grounds during late 1941 confirmed the anti-fragmentation effect as anticipated. However, test personnel observed something unexpected in the armor plate analysis. Entry perforations from covered projectiles displayed unusual angular characteristics. The holes were not elongated in the direction matching the shell's flight path, as engineering predictions suggested. Instead, they appeared more perpendicular to the plate surface than the impact angle should have physically produced. The projectiles were normalizing, rotating toward perpendicularity during the microscopic time intervals between contact and penetration. Nobody immediately comprehended the underlying physics. The phenomenon was documented, but remained unexplained. German test documentation from December 1941 notes unexpected penetration performance against angled targets without providing theoretical justification. Soviet intelligence obtained several of these reports through espionage networks, but initially dismissed them as exaggerated German propaganda. designed to demoralize armored vehicle crews. By spring 1942, the reality was undeniable. Cap projectiles were defeating Soviet sloped armor far more effectively than mathematical calculations predicted. The T-34's supposedly revolutionary protection was being systematically penetrated at ranges where uncapped shells would have harmlessly ricocheted away. The Wehrmacht designated these new rounds Panzergranate 39, armor-piercing shell type 39, and began mass production operations. Within months, German manufacturing facilities were producing hundreds of thousands monthly. The industrial capacity to manufacture soft-capped rounds would determine who controlled the Eastern Front's armored battlefield. The workshop at Friedrich Krupp in Essen operated continuously around the clock. Engineers hunched over metallurgical microscopes, examining cross-sections of failed projectiles. Each shattered shell told a story of extreme stress concentration, brittle failure, catastrophic fragmentation. The hardened steel heat treated to resist deformation during penetration was too hard. Carbon content exceeded 0.7%. Rockwell hardness measured above 60 on the C scale, perfect for cutting through armor, terrible for surviving impact shock. Dr. Herman Miller, the lead metallurgist, described the problem in his November 1940 report, stating projectile tips fracture at the moment of contact with hardened plate before significant penetration occurs. The kinetic energy dissipates through fragmentation rather than penetration. Velocity above 823 meters per second consistently produces complete projectile failure. The team required a cushioning mechanism, something to absorb the initial shock without compromising the penetrator's ability to continue through the target. Naval artillery had solved similar problems decades earlier with armor-piercing caps on large-caliber shells, but those caps were designed for projectiles measuring 280 to 380 millimeters in diameter, fired at much lower velocities. Scaling the concept down to tank gun calibers, 50 to 88 millimeters, required completely different engineering approaches. The first prototype caps were machined from mild steel, with 0.3% carbon content, but proved too soft. The caps compressed completely on impact, becoming a flat disc that actually increased the projectile's frontal area and reduced penetration capability. The second iteration used medium carbon steel at 0.5%. Better, but still inadequate. The cap would deform correctly, but then separate from the penetrator body during entry, again reducing effectiveness. Success came from differential hardening techniques. The cap needed to be soft enough to deform without shattering, but hard enough to remain attached to the penetrator during initial plate contact. The solution was a graduated heat treatment process. The cap's outer surface was left relatively soft, while the base where it attached to the projectile body was hardened. The cap could mushroom outward, while maintaining structural integrity at the connection point. But something unexpected happened during testing. When test officers fired capped rounds at plates angled 60 degrees from vertical, penetration exceeded all predictions, not by margins that could be explained by reduced shattering. The shells were penetrating sloped armor as if it were nearly perpendicular. Measurements of the entry holes confirmed impossible geometry. The shells were entering at angles significantly different from their flight trajectory. The cap was rotating the shell. Mechanical analysis revealed the physics. When a cylindrical projectile strikes a sloped surface, contact occurs first at the lower edge. The deforming cap creates asymmetric resistance forces. Pressure at the lower contact point exceeds pressure at the upper edge because the cap material is compressing more on the side that hits first. This pressure differential generates a torque around the projectile's center of mass. The shell pivots toward perpendicular. The effect was most pronounced with larger caliber rounds. An 88mm projectile normalized approximately 5 degrees on a 60-degree slope. A 50mm round normalized only about 3 degrees. The difference related to the projectile's moment of inertia. Larger shells had more rotational resistance, but also more cap surface area to generate normalizing forces. Wind tunnel tests at the WW2 for Luftfahrt in Berlin revealed a second problem. The stubby cap destroyed the projectile's aerodynamics. Muzzle velocity was excellent, but velocity degradation over distance was catastrophic. At 1,000 meters, capped shells were traveling 200 meters per second slower than uncapped rounds fired from the same gun. This reduced long-range penetration despite the anti-shattering benefits. The solution was obvious: add a second cap, a streamlined ballistic cap over the armor-piercing cap. The ballistic cap would be a thin-walled cone, aerodynamically optimized, that would shatter on impact without affecting the AP cap's function. German engineers designated this configuration APCBC, armor-piercing capped ballistic capped. But manufacturing was expensive and complex. October 6, 1941, near Mtsensk, Soviet Union, the German 2nd Panzer Division encounters massed T-34 formations for the first time. Hauptmann Klaus Weber watches through his Panzer IV commander's cupola as a T-34 crests the ridgeline 400 meters distant. The Soviet tank's frontal glacis presents at approximately 45 degrees, textbook deflection geometry for conventional anti-tank rounds. Weber's company has been briefed on the new ammunition, Panzergranat 39, shipped from depots only 3 weeks prior. Capped rounds, his gunner confirms. The first shot strikes low on the T-34's glacis. Weber expects to see the familiar spark of a ricochet, the shell tumbling away into the tree line. Instead, there's a dull impact, a spray of armor fragments from the exit hole. The T-34 lurches to a stop. Smoke pours from the driver's vision port. The crew hatches don't open. Did that just penetrate? The loader's voice cracks with disbelief. Inside the T-34, Lieutenant Dmitry Sokolov is dead. Before his brain processes the hull breach, the German shell entered at what should have been an impossible angle, normalized through the sloped plate, as if the armor were vertical. Fragments from the penetrator and armor spalling filled the crew compartment at supersonic velocity. The driver, sitting directly in the projectile's path, was killed instantly. The hull gunner lost his left arm. No one escapes. Weber's company destroys 6 more T-34s in the next hour, all with frontal hits against sloped armor. Soviet doctrine had emphasized using the glacis as primary protection, presenting the sloped front to enemy fire while maneuvering. That doctrine is now a death sentence. Every tank that turns to face the Germans receives a penetrating hit through its supposedly impenetrable frontal arc. Soviet battlefield reports are frantic. Enemy shells penetrating at previously safe angles. Sloped armor providing no defensive advantage. Request immediate tactical guidance. The messages flood into Stavka headquarters in Moscow. Soviet armor doctrine is collapsing in real time. Engineers who designed the T-34's protection system are summoned to explain how 45mm sloped plate is being defeated by weapons that should barely scratch it. No one has answers initially. The metallurgical analysis takes weeks. Recovered German shells show the telltale mushroomed cap, the deformation pattern that reveals the normalization effect. Soviet engineers run their own tests, firing captured German rounds at T-34 armor plates set at various angles. The results confirm the impossible. Capped shells are normalizing 4 to 5 degrees toward perpendicular, effectively reducing the protective value of sloping by 30 to 40%. German forces press the advantage aggressively. Tank commanders who previously avoided frontal engagements with T-34s now actively seek them. The sloped armor that was supposed to multiply protection has become a vulnerability. Soviet crews begin presenting their turrets, less sloped but thicker, rather than their glacis plates. This exposes the thinner side armor to flanking fire. Casualties mount catastrophically. In the Kursk operation of 1943, 40% of Soviet tank losses will be attributed to German 75mm guns using capped ammunition. another 26% to the 88mm. The uncapped rounds that dominated the war's first months account for less than 15% of kills. The remaining losses are mines, mechanical failure, and artillery. The soft cap has reversed the armor advantage completely. Soviet tanker Ivan Petrov, a T-34 commander who survived Mitsensk, later wrote in his memoir that they thought their slopes made them invincible. They presented their fronts to the enemy like matadors with capes. Then the shells started going through, not glancing off, through with clean holes in and clean holes out. The armor might as well have been vertical. German after-action reports note unusual crew behavior. Soviet tanks that would normally advance aggressively are now hesitating, angling their hulls in ways that expose thinner side armor but present the turret face-on. Commanders are panicking, abandoning decades of armor theory in favor of improvised tactics. The psychological impact matches the physical penetration. One innovation has cascaded into tactical chaos. The war is changing fundamentally. By mid-1942, German factories were producing capped ammunition at unprecedented scale. Krupp's Essen plant alone manufactured 400,000 Panzergranate 39 rounds monthly. The Friedrich Flick concern's metallurgical works in Hagen added another 250,000. The Deutsche Edelstahlwerke in Krefeld contributed 180,000. Total production across the Reich exceeded 1 million rounds per month by August 1942. Every Panzer IV, Panther and Tiger received priority allocation. Even towed anti-tank guns were re-equipped with the new munition. The Soviet response was industrial and doctrinal. Stavka issued Emergency Directive 0428 on November 17, 1941. All tank production facilities will immediately prioritize increased armor thickness over production volume. The protective value of sloping against modern ammunition is reduced. Compensate with additional millimeters. But the Soviet war economy was already strained. Adding armor meant reducing production rates. The factories that built 40 T-34s daily could only produce 32 with increased protection. Stalin refused to accept reduced output, stating they need quantity, armor is secondary to numbers. If the Germans can produce 1 million shells, they will produce 3 million tanks. The logic was brutal, but sound. Even if capped ammunition defeated individual tanks more easily, overwhelming numerical superiority would prevail. Soviet doctrine shifted toward mass assault tactics, accepting higher casualties in exchange for breakthrough momentum. Intelligence networks scrambled to understand the German advantage. Soviet spies in the Krupp organization obtained partial specifications for the Panzergranate 39. By January 1942, the technical drawings showed the soft cap construction, the differential hardening, the ballistic windscreen. Soviet metallurgists attempted to replicate the design using domestic steel grades. Results were inconsistent. Russian nickel-chromium molybdenum alloys performed adequately, but supply shortages forced substitution with inferior manganese-silicon steels. These substitute alloys were more brittle. Testing at the Kubinka Proving Ground revealed catastrophic problems. Soviet-made capped shells would shatter on impact against highly sloped armor, exactly the failure mode the cap was designed to prevent. German shells normalized and penetrated. Soviet copies normalized but fragmented. The metallurgical precision required for effective cap construction exceeded Soviet industrial capabilities in 1942. Production quality varied wildly between factories. Shells manufactured at the Stalingrad tractor factory showed 60% effectiveness. Those from the Uralmash plant achieved 85%. Rounds produced at the Krasnoye Sormovo facility in Nizhny Novgorod shattered 90% of the time. The Soviet solution was to abandon capped ammunition entirely for most calibers, and instead increase gun velocities and projectile weights. The T-34-85, introduced in 1944, mounted an 85mm gun with a muzzle velocity of 792 meters per second. This was below the 823 meters per second shattering threshold, but still delivered adequate kinetic energy through sheer projectile mass. The new round weighed 9.2 kilograms compared to the earlier 76mm 6.5 kilograms. Physics compensated for metallurgy. Soviet engineers prioritized what they could mass produce over what they could engineer perfectly. Strategic implications rippled across all fronts. Anglo-American forces examined, captured German ammunition, and immediately initiated their own development programs. The British 17-pounder gun received APCBC rounds by late 1943. American 76mm tank guns adopted the M93 hypervelocity armor-piercing round with capped configuration. In 1944, testing at Aberdeen Proving Ground showed the M93 could penetrate 2.5 times its caliber at close range, exactly matching German performance figures. The soft cap had become the global standard. By 1944, every major combatant nation except Japan had transitioned to capped armor, piercing ammunition for anti-tank roles. The final large-scale test of normalization technology came in Korea 1950. American M4A3E8 Sherman tanks, mounting the 76mm M1A2 gun, encountered North Korean T-34-85s near Pusan. The Shermans fired M93 hypervelocity armor-piercing rounds, the post-war American version of APCBC technology incorporating all lessons from German designs. Engagement ranges varied from 400 to 1,200 meters. Results were decisive. Of 97 T-34-85s destroyed by tank gunfire in the first month of conflict, 76 were penetrated through frontal armor. The M93 APCBC rounds normalized effectively against the T-34's sloped plates, achieving penetrations that would have been impossible with 1941-era uncapped ammunition. American after-action reports noted frontal engagement is now tactically viable against Soviet-design armor. But by 1950, the technology was already obsolete. The British had introduced the APTS, armor-piercing, discarding sabot, in 1944. This design used a sub-caliber tungsten penetrator wrapped in a full-caliber sabot that separated after leaving the barrel. Without a cap, without normalization effects, APTs relied on extreme velocity and reduced cross-sectional area. The British 17-pounder firing APTs could penetrate 231 millimeters of vertical armor at 1,000 meters, nearly double the performance of APCBC technology. The soft cap revolution lasted barely a decade before technological advancement rendered it secondary to velocity-based penetration systems.